Welcome to my class, and our subject is Electronics 3, also known as Industrial Electronics. I am Engineer Ivy Ramos, and we are going to discuss the topics under the prelim. Okay, let's review. So we have the previous topic from your last semester regarding the transistors. What are the transistors? Transistor is a three-layer semiconductor device which is used mainly for amplification and switching. There are some biasing that you can do where you can convert a simple transistor into different functions like switch and amplifier. Two types of transistors, mainly the BJT transistors that we have NPN and PNP, and we have the terminals of the base, emitter, and the collector. While Thyristor is a four-layer semiconductor device which is used for rectification and switching. So both of the two have the purpose of switching. But the difference is transistor is for amplification while the thyristor is for rectification. What is the difference between the two? Then we will look after what is the difference between the amplification and rectification. Power handling capacity. Thyristor is more capable for power handling rather than the transistor. Then current and voltage rating. Thyristor have high current and voltage rating while the transistor have low current and voltage rating. Internal losses. Thyristor have less as compared to transistor, and transistor have more compared to thyristor. That means when we use thyristors, we have the capability for minimizing the internal losses compared to transistors. Turn on and turn off time. Transistors takes very less time to turn on and turn off, while thyristors requires more time to turn on and turn off. Usually, thyristors need another device or another component to trigger the turn on and the turn off. Cost. Thyristors are costly, while transistors are cheap, thus economical and use several applications. That's why in our daily life, we are more aware of transistors rather than the thyristors because thyristors are expensive. Thyristors are bulky while transistor is light in weight. Thyristor, in terms of triggering procedures, needs just a single pulse to switch it to a conduction state, while transistors needs current continuously to keep it in a conduction state. That's why I mentioned before that thyristors need triggering device. Once you trigger it, it will continuously conduct. While in transistors, you need to continuously apply the current for it to continuously do the conduction state. We have high frequency application. Thyristors are not suitable while the transistors are suitable. In high power amplification, thyristors are suitable for high power applications while transistors are not suitable for high power applications. Based in this definition or comparison of high power applications, thyristors are more capable to handle high power with less noise, but it is bulky. Okay, so this is the comparison of the two electronic devices such as the thyristors and the transistors. So let's go to my slide for thyristors. My reference is Electronic Devices by Thomas Floyd. What is thyristor? Thyristors are a class of semiconductor device characterized by four layers of alternating P-N material. We know what is the P, what is the N material. So that means if you layer P, N, P, N, then you produce a thyristor. So four-layer device act as either open or closed switch. For this reason, they are most frequently used in control application. some thyristors and their symbols, I can accept this 4-layer semiconductor. Then we also have SCR. We also have diac, triac, and SES. 4-layer diode. We have a 4-layer diode. From the electronics 1, we learned that diodes have 2 layers only. That is the P and the N. That is either silicon diode and germanium diode. And it can be either varactor, what else? Zener diodes. Those are 2-layer diodes. But we have a 4-layer diode. And that is under the category of thyristor. We call it Shockley diode. Shockley diode is a type of thyristor that acts something like an ordinary diode but conduct in a forward direction only after a certain anode to cathode voltage called the forward breakover voltage is reached. Remember the term forward breakover voltage because you will continuously hear that forward breakover voltage for the following topics. The basic construction of a 4-layer diode and its schematic symbol, as you can see here. This is the internal construction, what is inside a Shockley diode. Shockley hindi Schottky. They are different diodes. Now we have anode at the P and the cathode at the N. So we have PN junction and this is the symbol. So a 4-layer diode has 2 leads labeled the anode and the cathode, and the symbol reminds you that it acts like a diode. It does not conduct when it is in the reverse bias. Because sometimes when that is in the reverse bias, there are times that you can damage the component. Okay. As a 4-layer diode, the concept of a 4-layer diode devices is usually shown as the equivalent circuit as PNP and an NPN transistors. So under the 4-layer, we have the combination of PNP and NPN connected in this particular manner. Ideally, these devices would not conduct, but when forward bias, if there is a sufficient leakage current in the upper PNP device, it can act as a base current to the lower NPN device, causing it to conduct and bring both transistors in the saturation. We know that in reality, there is no ideal component. Even if it's in the reverse bias, the current will still flow. So that means either forward bias and reverse bias, there will be a flow of current. But during the reverse bias, we have to identify the leakage current for it to be able to make the device in the saturation mode. The usual connection shown uses positive feedback. Any change in the base current of the Q2, base current here, is amplified and fed back to the Q1. If this current here in Q2 is magnified, it will feed back it to Q1. This positive feedback continues changing the base current of Q2. Both transistors go to either saturation and or to cut off. Meaning, if the base current of Q2 fed back to Q1 to magnify the original change, that will cause the device into a saturation or cut off. The only way to turn on the device is by breakover or the breakover voltage. This means using a large enough supply voltage to break down the Q1. We have to break down the Q1 or the collector diode since the collector current of Q1 increases the base current of Q2. Collector and the base. Since the collector current of Q1 increases, the positive feedback will start. If the current of the base here in Q2 is large enough to produce a positive feedback to the base of Q1, that will cause the device making it in saturation or cut off. And when we consider the breakover voltage, large enough to break down the collector of Q1. Once you break down the collector of Q1, then the positive feedback will start. That will be the conduction state. Meaning, we have to remember that the characteristic curve of a 4-layer diode shown below here is a forward blocking region. When the anode to cathode voltage exceeds breakover voltage, conduction occurs. The switching current at the point of IS. Okay? During the time that the breakover voltage is not met, it is in off state. But when the saturation current is met, the device will switch on into conduction. Once the conduction begins, it will continue until the anode current is reduced to less than the holding current. This is the only way to stop the conduction. Again, for you to be able to produce a conduction in the 4-layer diode, we have to break down this region. How do you do that? When you reach the breakover voltage, this J2 or the junction 2 will be broken so that the current from anode to cathode will pass. It will continuously conduct. The only way to switch off the Shockley diode is to lower the voltage or the applied current at the anode here for it to be able to reform the junction 2. Once you reform the junction 2, that's the time that it will only turn off. It's not that you just turn off the switch and it's turned off already. No, you have to go at a certain point where the junction 2 will be met for it to be turned off. Forward biasing. How to do the forward biasing for a Shockley diode? When the voltage is applied such a way that the anode is made positive with respect to the cathode, junction 1 and junction 3 are forward biased. The 2 base emitter junction is forward biased and the junction 2, which is the collector base, is reverse biased. Until the voltage across the diode is less than the breakover voltage, as an open switch Shockley diode exhibits a very high resistance and allows no current to flow through it. Once the breakover voltage is reached, as the forward voltage is increased, it exhibits a very low resistance due to the breakdown of junction 2. Therefore, it acts as a short circuit and allows the current to flow until the current reaches the holding current level of the diode. On state, current flows only when the voltage is more than the breakover voltage. During the forward biasing of the Thyristor or the Shockley diode, we need to eliminate the junction 2 or we need to break down the junction 2 in order for the Thyristor to work. That's why both the base emitter junctions of the junction 1 and junction 3 are forward bias and the collector base junction is reverse bias. By applying the forward or making this structure where the positive to anode and the negative to cathode, you are breaking down the collector base so that the flow of the current will be from anode to cathode. Then we have reverse biasing, meaning we are connecting the anode to the negative terminal of the battery and the cathode to the positive terminal of the battery. What will happen? When the anode is made negative with respect to the cathode, the junction 1 and junction 3 are reverse bias and the junction 2 is forward bias. If the reverse bias voltage is increased beyond the breakdown voltage of the Shockley, junction 1 and junction 3 are reverse biased, then the reverse current will flow through the diode. This reverse current produces the heat. Further, it could ruin the entire diode. Therefore, Shockley diode should never be operated in the reverse bias condition with the voltage equal to the reverse breakdown voltage. That means we cannot mistakenly connect the Shockley diode in the reverse bias because If the reverse breakdown voltage is met during the reverse biasing, it will ruin the Shockley diode. But how do we turn off the diode? Once the Shockley diode is turned on, it acts like a closed switch, offers a very low resistance to the current flow. To turn off the diode, the applied voltage must be reduced to a value such that the current flowing through the diode is less than the holding current of the diode. In this state, the junction 2 comes from reverse breakdown state and restores its high resistance value. When you lower the applied voltage of the Shockley diode, it will gradually turn off the diode since we are building up again the junction 2 of the diode. Applications. Shockley diode used as a relaxation oscillator. When the battery of the voltage is applied to the circuit, the capacitor charges through the resistance R. When the applied voltage across the capacitor is more than the breakover voltage of the Shockley, it becomes turned on and acts as switch. This causes the rapidly discharge of capacitor through the diode. When the current through the diode is less than the holding current of the diode becomes turned off and the capacitor charges again. The voltage across the capacitor is breakover voltage where the voltage at the reference is more than 0 volts because of the capacitor will not discharge completely. We also have Shockley diode used as trigger switch. We can use Shockley diode as a triggering switch for an SCR. Most common application of the Shockley diode are switching circuits to turn on the SCR. For example, this one. I will show you the circuit for the simulation of the Shockley diode during the oscillation mode. As you can see here, this one represents the Shockley diode because again, we need to connect two transistors by the definition of a 4-layer where we need to connect the collector of transistor 1 to the base of transistor 2 and the collector of transistor 2 to the base of transistor 1. So during the forward bias, this is the anode and this is the cathode. During the forward bias, the flow of the current will pass through the diode. So it will act as switch. As you can see here, the current across the resistor here is more or less 15 microampere. Yun, 14.4. Now, if we turn off, then it will discharge the capacitor. See, the flow of the current is backward. Then we turn on again, it will flow again there. Then you can turn off the Shockley diode by gradually decreasing the supply voltage. So let's say we gradually decrease, will it turn off? See, yes, it turned off. So that is how the Shockley diode works, okay? Now, here it is showing a negative flow, but again, in reality, we cannot do that in a Shockley diode because it will ruin the circuit. As you can see, the reverse bias is operating, applying a negative voltage. Here, the Shockley diode is not performing. During the time of oscillation that it has a negative feedback, it will discharge. Okay? Then when we go back to the original, when we increase it again, it gradually increases and it will maintain the value. When we switch this off, switch this on, doesn't meet the required here. That's why it's flowing through the capacitor. Doesn't meet the required breakover voltage for the Thyristor. That's why it's not yet flowing freely. We need to increase the voltage. When we go back to 15, see, when I turn this to 15, the flow of the current is flowing through the diode. Okay, that is how a Shockley diode is functioning. Okay, by the way, this is the everycircuit.com, where you will have your activities for this subject. Any questions? We finished for the Shockley diode. Then the next topic will be diac and triac. Okay? Thank you.